The Silicon Blueprint, Engineering the 2026 AI Infrastructure Megacycle. This presentation examines a provocative thesis that artificial intelligence infrastructure is approaching the physical limits of terrestrial computing and that the next phase may extend beyond Earth. The analysis connects advanced silicon, resilient supply chains, agentic inference, energy constraints, and orbital compute. Several market figures and company scenarios are forward-looking claims from the source material and should be understood as projections, not established outcomes. The blueprint begins with three infrastructure pillars. First is the hardware supercycle, next-generation GPU and TPU architectures, 3-nanometer fabrication, high-bandwidth memory, and wafer-scale integration. Second is supply chain decentralization, including foundry diversification, critical material resilience, domestic production, and reduced geopolitical concentration. Third is orbital compute, low Earth orbit systems designed for distributed processing, broad global access, and secure communications. Together, these pillars frame AI not simply as a software cycle, but as a heavy industry build-out. The paper next describes a memory and compute seesaw. Early investment concentrated on accelerators, assuming raw computation would remain the principal constraint. The argument here is that storage and memory capacity are becoming equally strategic. Enterprise-grade NAND flash must support larger models, retrieval systems, persistent agent memory, and rapidly expanding data volumes. The source highlights Kioxia as a symbol of this shift and cites dramatic valuation, earnings, and pricing forecasts. Those specific 2026 figures require independent verification, but the broader point is clear. Faster processors create little value when data cannot be stored and moved efficiently. The workload itself is also changing. Traditional artificial intelligence followed a relatively linear pattern: train a model, submit a prompt, and receive an answer. Agentic inference introduces a continuous loop. A system observes, reasons, acts, stores memory, evaluates the result, and corrects its next action. This increases demand across the entire infrastructure stack. Compute must remain available for longer sessions. Storage must preserve context. Networks must connect tools and data. And central processors must coordinate increasingly complex workflows. The result is a transition from occasional model queries to persistent digital operations. This transition may also reshape the central processing market. The paper points to growing demand for ARM-based AI infrastructure processors and cites major cloud and internet customers. It also identifies an export control challenge. Restrictions designed around accelerator performance and memory bandwidth may be harder to apply to general-purpose CPU products. That observation is attributed to ARM leadership in the source and should not be interpreted as legal guidance. Strategically, the message is that AI infrastructure policy must account for complete systems, not only the most visible graphics processors. NVIDIA's architecture trajectory illustrates the changing workload. Hopper established a foundation for large language model training and conventional inference using HBM3 and FP8 precision. Blackwell expanded scale with dual-die designs, mixture of expert support, and lower precision FP4 computing. The paper positions Vera Rubin as the next stage, pairing advanced accelerators with an ARM-based Vera processor and HBM4 memory. Its intended focus is reasoning, agentic AI, and continuous serving. In short, the architecture is evolving from training individual models toward operating always-on AI factories. I consider moving compute beyond Earth. The first pressure is thermodynamics. Dense accelerator clusters produce immense heat, and cooling systems consume energy, water, space, and capital. The second pressure is electricity. Gigawatt-scale data centers already challenge generation capacity, transmission lines, and permitting schedules. The source imagines future deployments on a far larger scale and argues that terrestrial grids may not expand quickly enough. The third pressure is geopolitical concentration. Advanced fabrication and packaging remain dependent on a limited number of regions and suppliers, creating economic and national security exposure. The proposed answer is not to abandon terrestrial data centers, but to add a new layer of infrastructure. Orbital systems could perform selected inference workloads close to satellite-generated data, distribute services across a global footprint, and draw power directly from solar arrays. The concept remains technically and economically challenging. Launch cost, radiation tolerance, hardware maintenance, network capacity, and orbital debris all impose serious constraints. The paper's value is therefore less a prediction of immediate replacement and more a framework for asking which workloads could eventually benefit from operating in space. The SpaceX case study is presented as a closed industrial loop. A localized fabrication initiative would supply strategic silicon and reduce dependence on overseas production. Starship would lower the cost of placing large payloads into low Earth orbit. Starlink would provide communications infrastructure and recurring cash flow. Terrestrial AI products would validate models and generate demand. Orbital Compute would then consume additional chips, reinforcing the manufacturing base. This is a conceptual scenario described by the paper. Partnership, revenue, customer, and valuation claims in this section should be independently confirmed before external publication. At the hardware level, the paper envisions modified satellite platforms carrying compact AI inference systems. Large solar arrays would benefit from strong, continuous exposure outside the atmosphere, while radiative panels would reject heat toward deep space. That could reduce dependence on terrestrial liquid cooling infrastructure. But passive radiation is not a free solution. High-power electronics still require large radiator areas, careful thermal design, radiation-hardened components, and reliable operation without routine physical access. The architecture is compelling precisely because it converts familiar data center problems into a different set of engineering trade-offs. The financial question is whether these systems can become economical. The source cites ambitious revenue, rental, loss, and valuation figures, but those claims are not independently established in this presentation. The more durable analytical point concerns portfolio risk. Launch vehicles, satellite communications, advanced manufacturing, and AI infrastructure can reinforce one another, yet each requires extraordinary capital and execution. A closed loop creates strategic leverage when its components succeed. It also creates concentrated risk when cost, schedule, or demand assumptions fail. Investors and operators must test every link independently. The final takeaway is straightforward. To own the algorithms of tomorrow, organizations may need to build the heavy industry of today. Competitive advantage in AI will depend on more than model quality. It will require semiconductors, memory, energy, cooling, networks, resilient supply chains, and potentially new computing environments. Orbital infrastructure remains speculative, but the constraints motivating it are real. The strategic task is to distinguish near-term bottlenecks from long-term possibilities, verify extraordinary claims, and invest in the physical systems that make digital intelligence possible.